This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So I remind you that this Thursday you have a midterm test, and this lecture is the last lecture that will be included in the test. So lecture 18. Just give these guys a bit of time to settle in. So everything that we presented so far, including this lecture, will be covered by the midterm test. Okay? All right, so you know you don't need to come to the lecture on Thursday. You just need to find a secure, good connection for Wi-Fi, compatible browser, so you can actually do the test. I believe that the practice test was uploaded. Is that right? So check that, how your browser works on that. That's a good test, just to see that you are compatible. We will have a head tutor, online if you experience any technical issues. You can't ask, head tutor to solve problems for you, but if you experience any technical issues, you can contact Jing. So Jing Mu that's the person who sent you the announcement about the test, okay? All right, so today I want to talk about internal model principle, which I briefly introduced in the last lecture. And we will talk about the principle itself, and then also how to reject disturbances if we're measuring disturbances. You know, disturbances are often signals that you can't measure, like a wind that hits the aircraft, or turbulence, or whatever, air pressures in front of the aircraft. You can't measure some things, but if you can measure, for instance, one example of a disturbance that can be measured is temperature outside the building. So that would be disturbance for the temperature in a room, right? Because the higher the temperature outside, the warmer would be in the room naturally, right? So temperature outside can be measured, right? So in cases when you can measure it, then we will learn how to do this disturbance rejection, canceling basically disturbance in a particular way. So note that this whole lecture is all about steady-state errors. So I would talk about tracking, but tracking for me would mean zero steady-state error. So I would like to track reference signals, basically maybe unit step references, with zero steady-state error, and I would call that tracking. Or I would like to track the references even if there are step disturbances or some other disturbances acting on the system. So whole lecture is about how to achieve zero steady-state errors under different scenarios. Here is the outline. So I'll first remind you that in the last lecture we had a particular view of integral control. So I want to revisit that because that's a nice introduction to internal model principle. And then I will present the principle itself. I will not prove things, I will just explain what the principle is. So the principle guides you in your selection of controllers. So controllers would have to have specific structure in order to yield zero steady-state errors for different reference inputs or different disturbance inputs. And then I will talk about feed-forward disturbance attenuation. So if we can measure disturbance, we can then attempt to cancel its effect directly in the closed-loop system. That's a different approach from internal model principle, but it's still a useful approach to know, right? So as a control engineers, sometimes you can measure disturbances, then you can use this approach. And then I will wrap up. So what's the motivation? Well, often we need to achieve zero steady state error. In other words, we may need to reject disturbances. That's what I mean, rejection of disturbance. Disturbance acts in your system, but you don't see its effect on the output, right? So by still achieving zero steady state error, right? Or sometimes we may want to track classes of reference signals. So I tell you, well, you need to design a controller that tracks these reference signals. Why can I know this? Well, that would depend on the application. So different applications can lead to different problem formulations. And often part of the problem formulation is to achieve zero steady state error for different classes of reference signals. It turns out that many inputs can be modeled in a very elegant manner as output of a system or transfer function with zero input. We saw that for integral control in the last lecture. We will revisit that and then generalize it in this lecture to state the internal model principle for more general classes of inputs rather than just step inputs. So what is the internal model principle? Well, the internal model principle states that the controller has to have specific structure to achieve tracking and disturbance rejection of signals that can be modeled in this manner. So what does this mean? If you have a specific, let's say, input, a reference signal like a step input, we would know that controller would need to have an integrator in it. You will see that this principle generalizes to other classes of inputs, like sinusoidal inputs or ramp inputs, etc. And every time, your controller would necessarily need to have a specific structure. So that's what internal model principle states. Right? So we will learn about that today. So revisiting last lecture, what we saw in the last lecture is that step reference inputs and step disturbance inputs can be modeled as the outputs of like transfer function blocks that have zero input applied to them. Then, basically the output of these blocks will be just due to the initial conditions of this system. So what we saw in the last lecture when we talked about integral control was that if we want to track step reference inputs and reject step disturbances, then controller necessarily needs to include the model of these disturbances. I would say that I'm modeling this reference input by 1 over S, and I'm modeling this disturbance input by 1 over S, and that model of disturbance or reference needs to be included in the transfer function. That model is internal to the controller model. That's why we call it internal model principle, right? Inside the controller model, we need to have the input model that we want to track or reject disturbance. So then we saw that if we have this controller structure and then we design B and A so that the closed loop system is stable, we would achieve zero steady state error for all references and disturbance inputs that are of this form. So that was concluded in the last lecture, and we just presented interpretation of the last lecture in this way. We did all the calculations, algebraic calculations, where we calculated zero steady state errors, and we proved the fact that this sort of controller's integral control action is needed in the controller to achieve zero steady state errors for reference step inputs and step disturbance inputs. Now, we want to generalize this, and the first thing would be to talk about more general classes of reference inputs and disturbance inputs. So what we want to do is we want to design a controller that rejects a class of references and disturbances, and we will assume that we can model these reference inputs and disturbance inputs in a similar way as we did in the last lecture. We will just replace this by something more general, and this also by something more general, and then we will see that a particular model of this and that would need to be included in the controller to achieve zero steady state errors. That's the internal model principle itself. So in order to do that, the first step is to explain how we can model classes of reference signals and disturbance inputs, and we will first talk about that. So in the last lecture, we saw that I can model constant signals or step signals as an output of an integrator with a 0 input. So note that the model of this integrator, when there is an input, if there was an input, the model of the integrator is x dot equal u, right? That's the model of the integrator. So if you find a transfer function of that, that would be exactly that thing. But when you set input equal to 0, you get this. But what is the sort of solution of this equation? Well, the solution, you integrate, this is dx over dt, right? So dx is equal 0. So dt times 0, when you take dt on the other side, you just get dx is 0. Integrate that from x0, right? You get that x of t, right, is all the time equal to x bar, which is the initial condition. So we generated in this way any step or constant disturbance as the output of this block. So we saw how to do this in the last lecture. Now we can now go through many more sort of classes of inputs, but that will be also motivating, you know, why do we model certain, you know, signals like this. So for instance, in a tram, the tram stops, there are some people on the tram, they get off, some people get off, some people get on, the mass of the tram changes. So, and that's an input that you basically can model as a step input. You know, the mass changes, and then the tram travels to the next stop, then again the mass changes. So all of these are like step inputs to the system. If we want to model a ramp signal, well, then the story is the same. If you consider, you know, double integrator, if we had an input here, then the model of that system would be x double dot is equal u. When I set u equal to 0, I get x double dot is 0. So if I integrate twice, I would find that depending on the initial conditions, you know, the output of the double integrator can generate ramp signals. Because you integrate once, then you integrate twice, and then you get a ramp, things that increase linearly with time. By the way, notice that here I assumed that x0 at 0 is 0, but if I assume something else, I could have gotten here a sum of a step signal and a ramp signal. So with a double integrator, I can generate step signals with certain choices of initial conditions, and I can also generate ramp signals in the same way as I did before, right? So where do we need ramp signals? Well, for instance, inertial sensors. What do inertial sensors measure? They measure acceleration. So often you want to figure out what is the velocity and position from acceleration. How do you do that? You integrate, right? You integrate the acceleration. It's basically x double dot, right? So x double dot can be integrated, and when you integrate it, you get something like this. So x double dot is measured. This is perhaps initial velocity is known. And then you can estimate velocity. You can also do estimation of the position itself. But my point here is if your initial inertial measurement, so inertial sensor measures x double dot acceleration. If your inertial sensor produces this measurement with a small constant bias, so which I modeled here as c. So instead of measuring x double dot, you're measuring x double dot plus c. This is sometimes called bias. So this bias is a non-zero value. It depends on your inertial sensor. And then when you integrate this, you get that your estimate here is basically, you know, the true value of the velocity, which is the integral of this guy, plus some ramp signal. So you can get ramp disturbances in your closed loop in this manner, if you are estimating velocity from acceleration. So in the room temperature example, if you have that the outside temperature can be approximated as a linear change over some interval of time, that's like a ramp signal. So from morning to afternoon, the temperature maybe gradually changes, roughly linearly. You can approximate it with ramp signals. So that's another example of a signal that can be modeled well by a ramp signal, right? Here is another one when the story is the same if you want to generate sinusoids, sine and cosine functions of a particular frequency. If I consider a transfer function like this, s squared plus omega squared, and I look at zero input, but then I look at different initializations By the way, the differential equation with zero input, if there was no zero input, then this would be u. But I set input to 0, then I get this differential equation. If I integrate this differential equation with different values of initial conditions, I can either generate cosine or sine signals also with different phases, right? Depending on initialization, I can generate different sines and cosines of different amplitudes, but the same frequency. Know that omega here is basically determined by the transfer function we use, but we can generate any amplitude, but particular frequency, which is determined by the transfer function. The same story. Where or how come we are interested in this sort of signals? Well, here is one example. If you have a disk drive servo mechanism, so there is a disk that needs to be centered, and there is a magnetic head that reads the tracks of the disk when you are playing music, for instance. This is now already old technology. But if you're looking at DVDs, watching DVDs or something, it's the same principle. So if there is any eccentricity, this thing is rotating. So there is a magnetic head that reads tracks, and then if the disk is slightly off center, since it rotates at constant speed, the sort of tracks would appear to the head as perturbed with some sinusoidal disturbance, right? There are many other examples where you can have sinusoidal disturbances. Some of them are listed here. Whenever you have some sort of rotating shaft, and then that's eccentric slightly, then that would generate some basically periodic sinusoidal, or maybe sum of sinusoids disturbances, right? By the way, if we have a sum of, if you think that your disturbance is like a sum of sinusoids, you can add these things up. So you can have s squared plus omega squared, omega 1, then s squared plus omega 2. So you can have several of these blocks generating different frequencies. So if you look at a general signal, you can look at first harmonics and approximate a signal using Fourier series expansion with finite truncation with finitely many frequencies. And then you can generate each of these frequencies in the same way. All right? This is a very cool example. Actually, I really enjoyed. So I went to this conference on control, and there was a plenary lecture. Plenary lectures, for people who don't know, is a single lecture. So for everyone in the conference would have to come to that lecture because that's the only thing happening at that time in the conference. Usually conferences have maybe from 5 to, I don't know, 20 tracks, parallel tracks. So you can see at any time 20 talks. But plenary lectures are so important that there's only one option that they give you. So everyone comes to the plenary lecture. So Alberto Isidori presented an internal model principle designed for a helicopter landing on a ship in high seas. So what happens is, it's a very cool problem. And by the way, they solved this problem using internal model principle, but they used the nonlinear model, much more complicated model for the ship than what we will use in our course. So imagine that your ship surface is like this, right? So helicopter needs to land, right? Now, when you are in the open seas, the ship moves maybe 15, 20 meters. These ships are massive, right? So movement of the ship depends on the waves, and you don't know the waves, right? Like what's the frequency of waves or anything. But what you can do is, you can, so if you wanted to land a helicopter on a ship with just pilot doing it, the helicopter is coming down to land, and the ship is sort of moving down, and the helicopter is chasing it, and then the waves push the ship up, and it crashes, literally crashes the helicopter. So what you can do is you can say, hover above the ship, measure the movement of the ship for a while, figure out the frequency of movement, then you figure out the internal model controller, then you apply the internal model controller, so you see how they have simulations. So helicopter is hovering, the ship is moving, and then helicopter first starts moving up and down, synchronizing and reducing the sort of error between the surface, and then it just nicely lands. It's a very cool application of internal model principle. So if you know, so obviously waves may have several harmonics. Maybe it's not a simple sinusoid. Maybe there are several sinusoids added, but you can figure that out also and then use the first few harmonics and still design a controller that gives you zero steady state error. Very, very useful, useful technique. All right. So we can now sum up what we know about disturbance modeling. So we can generalize everything, all these examples that we've seen. We will in particular consider input models of the form, you have some sort of transfer function where this gamma is called generating polynomial. So it's like a denominator of this transfer function generating the disturbances. And, you know, the generating polynomial is given by just some, you know, real polynomial with real coefficients, right? So note that the poles of this transfer function are zeros of the generating polynomial, and typically we pick those to generate different classes of disturbances or references. So for the integrator, gamma was just S, right? So when we were talking about step disturbances, then generating polynomial just S. For a ramp, what was it? S squared. For sines and cosines, what was it? S squared plus omega squared, where omega is the frequency of the periodic signal we want to generate. You can generate these generating polynomials by products of, let's say, S times S squared plus omega squared. That would generate, for different initializations, both step signals and sinusoids of frequency omega. So you can generate, you know, classes, large classes of inputs in this way. What's interesting is that none of these examples I gave you have poles, or, you know, like or zeros of this generating polynomial that are in the left half plane. Integrator, S equals 0. So it's on the imaginary axis. If we think about generating polynomial for the sinusoid, it's S squared plus omega squared, then it's plus minus j omega. Again on the imaginary axis. Double integrator S squared, two poles at the imaginary axis. So actually we will never want to have, I mean, these signals that converge to 0 are not interesting. Why are they not interesting? If I have an exponentially converging signal to 0, the signal exponentially converges to 0. I have a disturbance, it starts from some value and it converges to 0. Why am I not worried about that? If the system is stable, eventually disturbance gets to 0, and then the system is stable on its own. It's as if there was no disturbance from that point when it converged to 0. So converging disturbances are not interesting. They're not challenging. This is a challenging situation, all right? This is a challenging situation. All right. So, as I said, note all of these examples. You know, we took roots of the generating polynomial to be exactly on the imaginary axis. And left half roots are not interesting for this reason. All right. So now I want to state the internal model principle. I want to basically tell you what structure of the controller you have to use and which conditions you have to satisfy to get zero steady state errors for classes of inputs that can be generated by these generating polynomials. So that's basically internal model principle. That's it. Right. So here it is. So consider a reference and disturbances that can be generated by some generating polynomial gamma, right? Then internal model principle states that to achieve reference tracking and disturbance rejection, in other words, zero steady state error, we need to have, it is necessary that controller has the following structure. So you have to have that inside the controller, you have this gamma polynomial, which is the generating polynomial for references and disturbances. All right? So it's necessary to have this controller structure. By the way, if you just have this controller structure, but controller does not stabilize the system, you will not have zero steady state error. So obviously, you also need to have a requirement that you pick this B and A so that the full system, closed loop system, is stabilized. So that's the next, a requirement. By the way, the integral control is a special case. So if you want to track constant references and reject constant disturbances, we have to have that controller has to have integral action. So in this case, gamma generating polynomial is just S. So we have integrator in the controller, right? And then B and A are chosen to stabilize the system. Without stability, you won't get zero steady state error, right? You have to have stability. But how would design proceed? You first figure out what the generating polynomial is for the disturbances and references you want to track and reject. Then you impose this structure on the controller. Then you design polynomials B and A so that the closed loop is stable. That's it. That's the internal model principle in action. That's how you would use it, right? Why is this so important? Well, it generalizes a lot the principle that you need integral control if you want to track step inputs. Here you have a very general result. It tells you how to track much larger classes of references and reject much larger class of disturbances. So what are design steps? First, identify type of reference signals you want to track. So that will give you one generating polynomial, gamma r. And then consider if any disturbances cannot be generated by gamma r and are acting on the system. So find generating polynomial for those disturbances. That's gamma d. Then you basically multiply gamma r and gamma d to get the overall generating polynomial. Impose the structure of the controller where gamma is now imposed to satisfy zero steady state error for these references and disturbances. And then you need to design B and A so that the closed loop system is stable. These are the steps that you need to follow to apply internal model principle, right? Are there any questions? It's simple to use. It's not so simple to prove. Actually, proofs of these results, were some of the most fundamental results in control theory. So a couple of Canadians provided geometric sort of interpretation in the 1970s. So this is relatively recent work, right? And nonlinear results are even more recent. They were developed in the 90s. So this is a very sort of new stuff, and we are already teaching this to students because it's so important. So note that controller still needs to stabilize the system. Without stability, you won't get any tracking. Now, internal model principle provides a structure for the controller that is necessary to reject disturbance. It will reject disturbance if the controller also stabilizes the plant, right, the closed loop. Note that disturbance model is part of the model of the controller, and models of each disturbance and references need to be included in the controller only once. If you have, so you remember when we were doing integral control, we said references are step signals and disturbances are step signals, but we didn't have a double integrator in the controller. We don't need it. Single integrator would do the job, because single integrator would model both disturbances and references, right? Okay, so just a few comments. So because now, whenever we introduce this generating polynomial, we can think of this generating polynomial as part of extended plant. So then it's really like we are augmenting the plant model with some extra poles that are right on the imaginary axis. Now these poles on the imaginary axis may create problems in terms of fundamental limitations, what is achievable. So in terms of overshoot, rise time, and things like that, you may have extra limitations, so you are achieving zero steady state error, but then you might not be able to achieve some things with your overshoot, rise time, etc. So these are the important, and sometimes you may need to say, okay, I may want to give up on zero steady state error, but because overshoot is more important, or rise time is more important. So there will be all these trade-offs that you need to bear in mind. This is very effective when we know just something about disturbance. We don't need to measure disturbance exactly. By the way, when I model disturbances, I just said they are constant. I didn't expect you to tell me what's the amplitude of the disturbance. what's the value of disturbance. I'm just saying this class of disturbances will be possible to reject with this structure of the controller. I don't need to know the disturbance. I just need to know that the disturbance belongs to this class. That's a very cool general result, right? It's a very cool general result. We do not measure disturbances, but we reject them. All right. All right. As I said, pretty much any disturbance, like the deterministic disturbance, can be developed in Fourier series, and then you can usually higher, order harmonics are small, or sort of Fourier coefficients corresponding to them are small, so you can approximate well, pretty much any signal with, finitely many sinusoids. And you can then generate them with these polynomials and reject approximately any sort of disturbance in this way. We are talking here about exact rejection. Exact rejection. We will learn later on, when we talk about frequency domain methods, how to attenuate, but not reject, attenuate disturbances that belong to infinitely many different frequencies. Frequencies in an interval. That's a much more powerful but different method, because these intermodal principal controllers exactly reject disturbance, right? All right. By the way, in some cases, the plant may contain the model of reference or disturbance. And there are some, I'm here saying this is left for homework. I would like you to assume that the plant has an integrator, but controller doesn't. And look then at the steady state errors that you get from reference inputs, step inputs, and disturbance control inputs. See whether integrator in the plant helps in both cases, disturbances and references. This is left for homework for you to understand, what needs to be done. If you include always the model of disturbance and the reference in the controller, you are fine. You are fine. But sometimes you don't need to, but it's tricky. So that's why I'm saying this is left for homework. Have a look at this example. It's very insightful. I think you will learn a lot. All right. Few comments. This is a robust method in a sense that, if there is a little bit of perturbation in the system, you will not sort of totally lose this property. So small perturbation in the system would lead to small errors. So everything is designed for nominal model, for disturbance model in the plant model, and then for the model you get zero steady state error. But if you perturb all these things slightly, then the error will be small, right? So that's the robustness. You won't lose stability or anything like that. So also this obviously, you might sometimes have that intermodal principle requires high gain control. So control sensitivity may have peaks, and that's undesirable. That may cause problems, but we will best analyze this in frequency domain methods, which we will start talking about from next week. All right. So we will also look at now how to deal with cases when we can measure disturbances, because in those cases you don't have to worry about the internal model principle. You can just reject disturbance, cancel it in some way. Your controller would just have a different sort of like part of controller or control signal would try to cancel the effect of disturbances that are measured. So that's possible when we can measure disturbances. So reference feed forward. So you remember that when we were talking about the feed forward sort of method for getting zero steady state errors, we were including a particular filter. And the filter in this case was the complementary sensitivity function T0 evaluated at 0, right? So you can generalize that. You can generalize that by requiring that the filter that you include here doesn't have to be just a constant signal. In the case of step references, we used constant gain to make zero steady state error. But in general, you can use a filter that's not constant, but then you need to satisfy that complementary sensitivity times the filter is equal to 1 at zeros of the reference generating polynomial. So this is like a principle that is slightly more general than the feed-forward compensation of step references that we learned. And recall, in the last lecture, we actually used this. We used that T0 times the filter is 1, and we got that the filter at 0 is 1 over T0, right? So that's exactly what we got. So this just generalizes slightly that case. All right, so how do we now reject measure disturbances? Well, what we're dealing with here is basically a situation where, you know, we are saying we can measure disturbance. Note that there is a huge difference between reference signals and disturbance signals. In room temperature control example, the reference signal is the knob on the wall. You set the desired temperature. You can measure that. You know what it is. So getting measurement of that is typically trivial. But you may not be able to measure disturbances. Measuring disturbances in the room temperature example means measuring outside temperature, measuring how much heat went through the door when I opened the door or when I opened the window. You know, so these things are very hard to measure. How much heat goes through the door when I open the door? How is there a draft in this house or whatever? You know, that's very hard to measure, right? But in cases when we can measure, then we can do different strategy for control design, right? So we can follow a different strategy. So, and by the way, if you can measure disturbance, because you have more information, you would expect that you can do a better job. Internal model principle would asymptotically reject things. But if you measure disturbances in this way, you might be faster in rejecting the effects of disturbance because you are measuring, you know it, right? So, and you know, some disturbances can be easily measured, but some disturbances are impossible to measure. Sometimes we just can't measure certain things. Our technology is not mature enough to measure things. Sometimes even if things are possible to measure, it's too expensive to measure. You are engineers. Every time you design a system, you will be constrained by the budget. And sometimes even if we can measure something, if the sensor is very expensive, forget about it, right? You have to go without measuring things, okay? All right, so what is the situation when we measure disturbances? So what I'm saying now is, here is disturbance here. I'm assuming now that the plant is sort of, transfer function is split in this way. And I'm just sort of providing a slightly more general sort of scenario where disturbance hits you here. Now, I am assuming that can measure disturbance D, and hence I can, you know, this is a strategy that is proposed here. I can filter that disturbance through transfer function GF. You can design GF, because now D is measured. I can design DF. That's part of the design, right? And then I can feed this into the controller, and the idea is to change the control signal so that when I pass to this guy, this output here would somehow cancel the effect of disturbance. So I would, in the closed loop, have the situation as if disturbance is not acting on the system. That's the idea. Now, there are lots of problems with this approach, and we will first, you know, look at what the equations say. So if you write what the output and input are, and you look at these transfer functions here, if you see what is happening in the, you know, transfer functions, you would typically like to have that the transfer function GF is minus a GIO, which is this guy here, inverse, right? Because if this signal here would have to pass through that guy here. So if GF is exactly that, then this signal here is multiplied, so this D times GF. Then if I design filter to be like this, then when I pass that signal through here, I will get here exactly minus D effect, plus something else, which is control closed loop action, right? So if you have this, then these two signals here would cancel the effect, and this signal here would be as if there's no disturbance acting on the system. right? But what are the problems with this? Well, there are several problems. First one is that typically this system here is a causal system. So it might have 2 poles, 1 0. It's a causal system. So what is the inverse of this? It's anti-causal. Inverse of that, there is 1 pole, 2 zeros. So realizing physically the inverse of a causal system is a big problem, right? You can approximately do it by adding fast poles, extra fast poles in the inverse. But then we are talking about an approximation. We cannot do it exactly because of causality, right, issues. Another problem is that if GIO had unstable zeros, right? It was maybe, this is maybe a stable part, but it had unstable zeros. These unstable zeros in the inverse would become unstable poles. So, but know that this guy here is running in open loop. It's not in the closed loop. So if you have an unstable system, there's a problem there because any error in measurement of D would amplify. You're passing some signal through an unstable system, things will go wrong. Any error would be amplified. So there is also the issue of stability. So because of this, I mean, and by the way, the last thing is that I didn't say is obviously I would design GF in such a way that, well, I'm using the model. But if the true system is different from the model, then again, I would not exactly cancel things. So I need to know the model well for this to work well, right? So not only do I need to measure disturbances precisely, but I also need to model very well in order to cancel exactly things, right? So that's yet another issue. So that's summarized here. So first approach is sensitive to modeling errors. Feed-forward transfer function needs to be proper and stable, right? So, and then there are all sorts of issues with high gain. Some of these we would better understand once we go to frequency domain methods. I listed these comments here for your reference, but once we go through frequency domain methods, you can go back and understand these better. I can't really sort of go through some of these, but they are here just for your revision. When you go back, once you covered all material, it will be very useful. All right, so I just want to wrap up things. So what we did in today's lecture, we showed that internal model principle can give you 0 steady state errors if the controller has a specific structure and you stabilize the system. The specific structure of the controller would depend on the type of disturbances and references that you want to track or reject. So every different case would lead to a different structure of the controller. This is a robust technique, but may require high gain. We will understand this much better when we do frequency domain methods. And we will revisit some of these things then. And then, obviously, when the disturbance is measured, we can use feed-forward control, but there are several issues with it. First, we need to know the model well. We need to measure disturbance. There is a problem with physical realizability because we may end up with an anti-causal filter that's necessary to cancel exactly things. And also stability of this filter may be an issue. So if it's unstable, if you get that the filter is unstable, you cannot implement it exactly as is, but you may implement its stable approximation or something like that. But that would then not exactly cancel disturbances anymore. So there are all sorts of issues with that design. All right, are there any questions? All right, well, good luck with your midterm. I mean, I'll still see you, but, I'm not sure whether you will be coming tomorrow. So, midterm on Thursday. And today I do have consultation time, so you're welcome to come and talk to me.
Yeah.
we won't have body parts. So we excluded it. Last year I reorganized the material, so there won't be, I told you, only things that are covered in the first 18 lectures. Because in the past I was presenting material in different order, but I changed it last year and I'm sticking out this.
40分钟，拿到了，那我不直接就超不了。知道吗？我们现在有一套。 真的换成那一套，哎，又打错了。对呀，不能串掉啊！这很奇怪吗？很多对呀，女生这种，其实等于通常也是有不是我在说，是我妈在说。 王家宝，当年你爸说的。